So we've been talking about the electric field created by a charge, and specifically due to a point charge. So the way the electric field has been defined, the electric field will point away from positive charges, radially outwards in all directions, and it will point towards negative charges. The electric field can be calculated for a point charge by knowing how much charge there is, the charge that's creating this electric field, and how far away from the charge that we're trying to calculate the field. K, remember, is our constant. It represents the 1 over 4 pi epsilon naught. So we can actually charge a multitude of objects. Objects don't have to be point charges, essentially. So, for example, when we were talking about charging initially, if I have some sort of rubber rod or plastic rod and we rub it with fur, we know that electrons, in excess of electrons, collects on this rod. And so we essentially have a whole bunch of point charges. Each electron would be considered a point charge, and all of them would be contributing to an overall electric field that would point towards the rod. At the end, we'd get some interesting directions going on, but the field itself is not spherically distributed like for a point charge up here. And so we need to be able to find the electric field due to these various different ways objects can be charged. So we're going to talk first about the charge density. There's 3 ways in which charge can be distributed. For this rod, for example, we could call this a thin rod, or it could be, not this one specifically, but we could have a wire of some sort that was charged. Essentially, the charge is along the length of the rod. The rod itself isn't particularly thick, so we don't have a wide region, a big distance for these charges to spread over like we would if we were talking the Van de Graaff sphere. In the case of charge along the length of something, we call this a linear charge density. If you recall, when we talk about strings and the waves on the string, we talked about a linear mass density, which was mass per length. Here, linear charge density is charge per length. Our author uses a lambda to represent this, which is not wavelength, so just make note not to confuse with wavelength, because that is what we recently used lambda for. So charge per length is this linear charge density, and that would apply everywhere along the rod that actually has an excess of charge. If you think about the Van de Graaff sphere, the conductor where all the excess charge goes out to the outside surface, it doesn't have to be just for a conductor, but conductors that have a net charge, the excess charge will always reside on the surface if we're in an equilibrium state. It will work. Insulators can totally have a charge spread over its surface as well. Either way, we call this a surface charge density. So on the Van de Graaff, this is a 3-dimensional sphere. All the surface has charge on it. So we call this a surface charge density. Our author uses the Greek symbol eta. This is the amount of charge per surface area. So if we were to chunk out a little surface of this sphere, that surface, that section, would have a specific amount of charge on it. It is common if you're using other resources, it is common to see sigma to represent surface charge density as well. So you might see that. The last way charge can be distributed is throughout the entire volume. That would have to be an insulator, because a conductor, if it has any excess charge somewhere in the middle, there will be a net force that in turn the electrons will end up moving until an equilibrium has been reached, and that puts the charge on the outside surface. So an insulator, somehow in the process of creating our insulator, it gets charged up everywhere throughout the volume. So we would have a volumetric charge density. We use rho to represent that. That's the same symbol we use to represent mass density, mass per volume, but now we're talking about charge, so this would be charge per volume. These densities, however the charge is distributed, will come into play in determining and calculating the electric field around any one of these objects. And so we want to build on that and find the electric field. We're going to start with something like a rod, because it's the easiest as far as integration is concerned, typically. Now, one side note really quickly, the problems that you are solving are going to tell you how the charge is distributed in some way. But another thing to keep in mind are the units, because that can be just a second way to make sure you are thinking of the charge distribution correctly. So remember, charge is in coulombs. A length would be meters. So the units of a linear charge density would be coulombs per meter. Similarly, if we come over to the surface charge density, the charge is in coulombs, but the area would be in meters squared. With volume charge density, we're going to get coulombs per meter cubed. So looking at units can be helpful as well. But in any of these situations, we can determine the overall electric field. So let's talk about a thin rod here for a second. So a thin rod or wire, we're assuming the charge to be distributed along just the length of the wire or rod. This charge could be positive or negative. I'm drawing it positive for no particular reason. It could very well be a negative net charge. The difference will be the direction the electric field points in. Now, let's just say we want to find the electric field over here, a distance, I'm going to just call it a distance A from the left end of this rod. I know a point charge the electric field it creates depends upon that charge itself and how far away from the charge the point that we're interested is located. So for example, This point charge right here is this far away from the point of interest, and it has a charge of, we're going to call this dq. If you remember in the previous video, if we wanted to find the total electric field due to multiple point charges, we simply added them together. We had to find E due to those, say, 3 charges. We added them up vectorially, and then the result was the overall electric field at the point we were talking about. That is still true here, but we're going outside the realm of just 3 or 4 charges. We have a whole bunch. The whole entire rod can be thought of as a whole bunch of point charges. And all of these are contributing to the electric field at this point down here. So when we start summing up more and more charges and their electric fields that they are creating, we essentially are getting an electric field by integrating what we call the electric field due to each individual point charge. So what I mean by dE here is this charge coming back to the rod, this charge, this infinitesimally small piece of charge. I don't know that I'm spelling this right. I apologize. Small piece of charge, meaning a point charge. dE represents this electric field at the point that that charge is creating. So this is the electric field created by dQ. So when you learned about integration, we were talking about adding small pieces. So like position, for example, we said was the change in velocity over change in time, but if we wanted an instantaneous position, we needed to take this as the limit of delta t goes to 0. That's where this became the derivative, which is totally the wrong equation. Good grief, I'm tired. Let's try that again. Velocity was the derivative of position with respect to time. That came from starting with dx dt and then talking about the limit as delta t goes to 0. So very, very, very small time increments so that we were accurately summing that little slope all of the time. And that became the derivative. What we're saying essentially in the same case is we're breaking this down into little teeny tiny charge segments. So not time segments, but charge segments. And each of those charge segments, each of them is contributing, so this would be another dq. It would also be creating its own dE here, but that dE, its electric field, would be smaller than the first one we drew, and that's because the distance now is bigger. As I continue thinking about going the entire length of this rod, I have another dq. It too would create an electric field here, but that would be even smaller because this charge is farther away. And so when we say the electric field is the integral of the electric fields that each piece of charge creates, ultimately we're saying that if we take the electric field of a point charge, where Q is represented by dq, any one of these little pieces of charge, and how far away they are from the point of interest. By adding all of these electric fields up, we can find the overall electric field at that point due to the entire length of rod that has charge on it. Okay, this might sound a little overwhelming at first. It's really not too scary. Remind yourself of that. We're simply adding together. That's what the integration represents, is summation. So we're adding all of these individual electric fields due to each little piece of charge. Now, the reason these electric fields due to all of these little charges, the reason they're different is because these distances are different. So each piece of charge is the same, but the distance from the point of interest is different. I'm going to draw the picture again. So the point I care about is over here, some distance A from the left end of this rod. Let's say we know the total charge and the total length. I'll write it this way. Of the rod. So meaning this rod is L long and capital Q is spread uniformly. I guess I need to say that as well. Uniformly charged. It doesn't have to be. We'll do an example where it's not. But here we have this uniform charged rod. We're saying we know the total charge Q, the total length L, and we want to find the electric field at this point over at the left. Okay, to set this up, we do need a coordinate system to work with. I'm going to go ahead and just say my x-axis is the axis the rod itself is lying along. And for simplicity's sake, I'm going to go ahead and put the y-axis through the point of interest. If the problem gives us a coordinate system to work with, we have to use their coordinate system. But if it does not, we can put it where we want. So the first thing I want to do is represent what I mean by DE. And what I mean by that is any one piece of charge. It has charge dq, and it is a distance r from the point where I'm trying to find the electric field. In this coordinate system, r would simply be x. Since I've put the point of interest and made that my origin, then any distance I measure to the right would be an x distance. So by DE, we mean the electric field created by DQ So DQ, right now, I'm just going to replace R with X. Because I know as I choose different pieces of charge, if I think through all of these charges, all of them are varying in distance from the point we're trying to find the electric field at. And so I'm essentially putting X in and saying X is my variable. So at the moment, what I can say is this electric field due to this rod is K, which is our constant, dq over x squared, and our hat, meaning the direction it will be in. So let's think about that here. Coming back to the original dq, I marked, this is a positive charge. The point of interest over on the left is going to have an electric field, and the electric field DE is going to point to the left because that is the direction that is away from this charge. Positive charges create electric fields that point away. So I can actually, coming back here, for this original piece of charge, say its direction is in the negative x direction, negative I hat. That works great. Now, before I plug that in for all of the pieces, I do need to consider all of the other pieces. So this DQ right here, it's creating a field over at this point as well. What direction is it in? Well, this charge is positive. Positive charges create electric fields that point away from them. So over at this point of interest, away is also still to the left. Because this is true for all pieces of charge, all of these individual point charges, I can come to my original equation up here, or the equation that I'm setting up, and I can put negative I hat in there for R hat. And that's because every single piece of charge on that thin rod is going to create an electric field that points to the left at that specific location. Okay, we cannot integrate yet. So if you remember with integration, the d whatever, dx, dt, dy, in this case dq, is telling me the variable that I would be integrating with respect to. Meaning everything else in the equation would have to be in terms of a constant or q. And that's not the case yet. We know x is varying. X is varying, thus it is our variable. Each piece of charge is a different horizontal distance from this point on the left that we want to find the electric field at. So what we want to do is to be able to write this dq in terms of dx. Because I cannot integrate with x as my variable until I have a dx. The nice thing is this relationship is always done in terms of those charge densities. So here we have a linear charge density. Lambda. That would equal this total charge over the total length, which I mentioned we're just going to assume we have this total charge Q and total length L. But this would also equal any small segment of charge over the length of that segment. Coming back to our picture, the length of any one segment, we're going to call it dx. Just a little delta x, little distance along the x-axis that particular piece of charge fills up. It's kind of like the idea of water having a density, and whether I have a bucket of water, a cup of water, a swimming pool full of water, if it's all the same water, the density is the same. We're saying this linear density is the same whether I'm talking about the total charge per length or just a section of the charge over the section length. What this leaves me with is that dq is lambda dx, or dq in this case, since we know lambda can be written as q over L, dq would be q over L times dx. And so now we have a relationship of dq to dx. So what I want to do is put this in to my equation for dq. So integral k is the same constant, dq is q over L times dx. We already made the substitution that r was equal to x, and the substitution that r hat was I hat for each piece of charge. So right now we have k, which is a constant. We are assuming we know this total charge and length. Oops, I forgot my negative sign on my I hat. Sorry about that. The direction is the same for all of them. So if I pull out everything that is a constant, that leaves me with 1 over x squared dx. This is an integral we can solve. Dx tells me my integration variable is x, and that's the variable I am integrating. Great, we don't have anything else in here that is changing. The one more thing we need, though, is some limits of integration. So dx is telling me we're going to integrate, so essentially along the x-axis in our picture. We're going to add up along the x-axis. Well, we're adding up where the charges are. So the first place we would see a charge would be at the left end of the rod. This represents the lower limit in our integral. So that is at location A, according to our picture. The integration takes care of adding. As we continue going in the x direction, we can keep going, but we only want to add up where there's actually charge. So this right end of the rod would represent the upper limit. So that would be A plus L. L being the total length of the rod. Okay, so just as a reminder, what we know is A, Q, L. These are the things we know, and we know it's positively charged. So when we come to this integral now, I'm just going to rewrite everything out in front. Integral of 1 over x squared dx, that's the thing, same thing as x to the negative 2. The integral of that is negative 1 over x. Our limits that we will need to plug in are between the lower limit of a and the upper limit of a plus L. I'm going to cross out or cancel out these negative signs right here. I would, I need my I hat. So 1 over a plus L, I put in the upper limit first, minus 1 over a, that's my lower limit. So the overall electric field at that point can be calculated knowing our constant, the 8.99 times 10 to the 9, Newton meter squared per Coulomb squared. The charge, the length, and A was how far from the end of the rod that the electric field will point. Now the negative sign will come back if we actually plug numbers in. For example, if we said we had a 25 centimeter thin rod on the x-axis between x equals, I don't know, let's make up some numbers here, 10 centimeters and x equals 35 centimeters. And it was charged uniformly with Q of positive 42 nanocoulombs. What is the electric field? At the origin. So just putting this in a picture of sorts, our rod, this guy here, is total charge of 42 nanocoulombs. This end is at x equals 10 centimeters. This end is at x equals 35 centimeters, which gives the length of 25 centimeters. Okay, so our setup, let's just make sure our setup makes sense. We're trying to find the electric field at this origin. We're told this charge is positive. So each little chunk of charge, each little point charge, is going to create its own electric field that points away from it, and to the left is away from the charge on the x-axis. So this setup is what we were just talking about symbolically, which means we would come to the solution I still have on the screen. So let's plug numbers in. So there's E. Our total charge is 42 nanocoulombs. The length is 25 centimeters. I want that in meters. We always want to watch our units. I have that I hat there. 1 over A plus L. Remember, that means this right end of the rod. That's the upper limit. So that's the 35 centimeters, but in meters. The A is the left end of the rod. That's how far from the origin we're talking about. So that's the 0.1 meter. So units alone, the meters in here, when they combine, times this gives us meters squared, which cancels with the meters squared in the constant K. This 1 coulomb cancels with that one. So we're going to end up with units of newtons per coulomb, which is what we should get. That's the proper units for electric field. Now let me plug these numbers in. I'm getting E is negative 1.1 times 10 to the 4th newtons per coulomb. And then that I hat is there. And notice we are getting that negative answer as expected. We accounted for that direction properly. Now, this is the same type of problem where you will want to be careful if the charge is negative. I would, coming back up, I would use absolute values when we're talking about Q over L. So Q, or even the linear charge density, I would always put in absolute values because you're accounting for the direction already. And you want to make sure you don't mess up the direction by putting in negative values for Q or lambda. So I'll go through a couple more examples. You do want to recognize when integration needs to be done. And that is going to be on a thin rod when the point you're trying to find the field at is not directly perpendicular from the middle. And I will review that again later.